Good evening, everyone. Welcome to the second episode of the IEEE CEDA Industry Insight Series. And today we are having the speaker, Mr. Lakshmanan Balasubramanian, is the ex-technologist and SMTS from Texas Instrument. And also today the topic is on the introduction to low power system technique. Before going deep into, I'd like to request Mr. Sajal Mittal, the chair of IEEE CEDA Bangalore Chapter, to share to address the gathering.
Okay. Hello, everyone. Thank you for joining the industry inspired lecture series. This is episode 2. And thank you, Mr. Lakshman, for agreeing to deliver this lecture. I think this topic is very apt according to the current semiconductor scenario because everybody wants high speed, high performance in the low power, and it's very tricky to achieve. I think Lakshman has a great experience in that. So please interact with him, listen to him, post your questions in the comment box, and looking forward to have a good interaction. And in future also, we keep on organizing these lectures once every month. So please join that as well. And as Vamsi mentioned in the beginning, uh, for all the lectures, you have the certificates which you can showcase at the different forums, but certificates are issued only to the SEDA members. As SEDA membership is free, you can go ahead and take the SEDA membership so that you will receive the certificates for the lectures. I won't take much time, and thanks again. Over to you, Vamsi.
Thank you, sir. And also today we have here Mr. Alok Das, the founding chair of IEEE CEDA Bangalore Chapter. I would like to request Alok sir to share a few words to the gathering. Alok sir.
Alok, are you there? Alok, you want to say something? It's okay, Vamsi. We can move forward.
Yes, sir. It may be some technical issue. So without going delay, let me introduce our today's speaker. So again, good evening, everyone. It's my pleasure to introduce Mr. Lakshmanan Balasubramanian, a seasoned analog and mixed-signal semiconductor expert with over 25 years of experience in design, verification, and silicon validation. He has contributed to more than 20 mixed-signal SoC products, including ultra-low power microcontrollers and advanced connectivity solutions, and spent nearly 2 decades at Texas Instruments, where he rose to senior member of technical staff. Lakshmanan is also a senior member of IEEE and currently serves as secretary of the IEEE 1801 working group, helping shape global low power design standards, and a chartered engineer and an active mentor. He is also deeply committed to both technical excellence and the engineering community. So please welcome me, please join me in welcoming Mr. Lakshmanan Subramanian. Sir, the stage is yours.
Can you see my video?
We can see your video. We can see your video, sir.
Okay, just give me a moment. I'm not able to.
And we are participating.
Where the mirroring happens, do you know? I'm sorry for the background.
Sir, inside the video button, you can see a laptop with the arrow icon, sir.
Correct.
Please click on that.
Yeah, I just added there, but just want to know where the mirroring part happens.
So can you click on the entire screen once?
Entire screen, you mean?
Yeah, yes, sir. Entire screen and select the screen, sir.
Okay. But anyway, yeah.
And click on share, sir.
Oh, okay. No, share part is fine. Okay, that's okay. Yeah. Are you able to see?
One message is coming. Yes, sir, we can see it. So we can close the tab, beside the tab.
Pardon?
You can close that one, sir, if you want, or else you can minimize.
Yeah, fine.
Okay, sir. You can take it.
You were able to see the screen, right?
Yes, sir. We are able to.
Okay. Thanks a lot, Sajal, Vamsi, for a kind introduction, and also Alok being here, and other CEDA members, and all the students that are joining here. Briefly, Vamsi, may I know, like, kind of, I mean, is it like predominantly students and we have industry members too?
Sir, around 70% are students.
Okay. Good. So I'll start with this. So basically, I'll have here a brief talk on introduction to the low power system design. Again, when we talk about system design here, it can mean a lot. We are primarily looking at electronic system design here, and we will have it like this. The outline will be, I'll start with a brief motivation of why low power design. Maybe I will give some introduction to the context of IoT as a background, which may not be necessary, but it will just give a motivation on why, linking to the real world problem, and then going to some concepts on low power system design and what's called a power intent, and then the low power design verification. This is not everything about low power design, but this is some of the basic things that one may want to start with respect to the low power design aspects. My audio is clear, right, Vamsi?
Yes, sir, it's pretty clear.
Okay. So as a need for low power, right, there has been an increasing demand on analog power management and RF integration in mixed signal SOCs. It has been a key trend. We will briefly talk about it. I mean, as we go forward, you will see examples of that. And especially the end applications areas like consumer electronics, personal medical electronics, etc., with also evolutions like the Internet of Things and Edge AI, drive a need for battery-powered operation with longer battery life, autonomous operation. We will come to what is autonomous operation very briefly, little later, low cost and low power, right? We will primarily look at in this presentation about the aspects of low power, the need for low power, and how to approach low power system design in a more formal way. There are multiple ways of doing things, custom way of doing things, how you approach the design in a more formal, systematic way. Right. So as a background, I would just like to take just few minutes, go into the field of IoT. Again, I won't get into the system design aspects and detailed circuit design and all of that. Just give you some set of applications, and from the applications can we derive some of the high-level requirements and the need for low power. Right. So this is again, the low power is not the need only for Internet of Things. I'm just showing this as an example. This just shows one way of defining, describing what is Internet of Things. What does it involve? It involves basically you have the sensors as eyes and ears, which collect data, right? And then you have the brain. The data collected is taken to the microcontroller unit, microprocessing units, and network of processor. The processing power of the system is what processes the data that comes from the environment through sensors and GPS, etc. And then once the decision is made based on the data processing, whatever action has to be performed is performed. The arms and legs of the Internet of IoT system are actuators. Like it could be motor, it could be other various other elements, transducers, electrical to mechanical or electrical to temperature or any other kind of thermal transducers that will do a necessary work, useful work. And obviously these are multiple of such devices. They will be employed for various purposes, and they will all be talking to each other, and hence there will be multiple communication protocols that may be applied. I mean, it's not limited to one, depending on the range, depending on the power requirement, etc. Various other requirements. There can be multiple wireless and wired communication, predominantly wireless. Of course, as a concept, wired communications are also supported, but predominantly, as you see, as you go further, you will understand why wireless communication is obvious, right? And then obviously there will be a software stack sitting on all of these top to run your applications and control them, right? Very briefly, what do they mean? Actually, Internet of Things are nothing but smart end equipments. Just give me a moment. There's some my screen. Just put it aside. Okay. So here, what are the high-level end equipment requirements for? When I again talk about end equipments here, these are edge equipments or end equipments, not really the hub or the server side or cloud side of the things. It's really the end equipments that the end user or application, the consumer is handling. This end equipments are sensor and actuator nodes, and they have to be smart with required processing power, and they're connected, as we already talked about. They are controlled. You should be able to, the user should be able to control as requires, and then they have to be intelligent so that like they are automated to do things. The user doesn't have to continuously necessarily monitor them for even routine stuffs. And obviously there will be security and safety aspects, which I will not get into the details in this presentation. Right? There are a variety of applications. I won't get into the details. You will see these are very well known for more than a decade, and I won't get into details of this. Of course, recording of this session will be there. You can go to the details. These are some application examples with references you can look at. Again, these are some the same applications I'm showing in a more pictorial form. These are examples of wildlife habitat monitoring, IoT, industrial IoT, industrial control, automation, and then agricultural, economical agricultural examples where you have multiple monitors of various parameters which have to be controlled, monitored and communicated and continuously monitored. And based on that, some action have to be taken. And this is an example of a building automation. As you see, there are multiple sensors and functions here. There is a slew of them. It's a sensor fusion. But again, I'm not going to point each one of them and explain what each of this do. It starts all the way from your digital video camera to various other things, including navigation, inertial and internal in-house navigation, indoor air quality services, smoke control, and whatnot, various of them. I'm not going to get into the details of all of this, just showing an example of where these multiple IoT nodes come together in the end application. Right? This is another example of an automated home, where in addition to the automation inside the house, obviously the house is powered by a smart grid. So the smart grid related applications also require a lot of IoT related applications, smart homes, smart grid, smart vehicles, and all of this are talking to each other. Right? There are also links to detailed application notes, case studies that are provided here. If you want, you can go through them offline to understand them in detail. But the details of any of this is not really important for today's talk to understand why low power and how to approach low power design. Okay. This shows biomedical instruments. This could be very small equipments. Some of them could be like implants, or some of them remain inside your body for a short period of time, and then but they have to wirelessly communicate, and then they get defecated safely. For example, a pill cam here. There are various such applications, or the BP monitor kind of things, which can be battery operated. But as you see here, what is one thing that's common about all of them is that this is an example of a structural monitoring, which actually is this is a Golden Gate Bridge, but any bridge would work here. You can take your Kerpuram Bridge, for example, or the Hosur Road Bridge. I mean, there's a long one. And obviously, all that many of us, we don't know about the infrastructure development. This generation is when a lot of infrastructure is getting developed. And soon, most of these have a lifetime of 50, 100 years or 200 years, right? So suddenly, some point in time, all the simultaneous development of infrastructure in India, it is good that we are seeing explosion of infrastructure. There will be a peacetime, and sometime in future, that all of this will have repairability, maintainability problems occurring. So how do we proactively handle this, right? When all of them collapse in day one, in one single day, of course, there can be catastrophe, but more than that, rebuilding and whole system will be chaotic, right? If we can somehow manage the catastrophe part also without being catastrophic. So how to manage them in futuristic way and in a preemptive way. So that will require a lot of sensors, vibration sensors, strain gauges, and all that, and talking to each other, and then continuously monitoring proactively. And whenever there is a deviation of required parameters, you can take decisions. It can be communicated to right decision makers, engineers, architects, and then you may take preventive action, protective action, so that their life can be extended, or any catastrophe can be avoided. So these are various examples. Again, with all of this, what do we see? Most of this are characterized by being physically isolated, right? So when you have so many sensors thrown throughout your bridge, or for example, in a wildlife habitat monitoring, or the RF collar, ID collar that are employed on individual animals and things like that, they cannot be wired. You cannot control them, that they have to be in a specific place, in an environment, in a specific location, and then there it will be deployed. No, once you deploy it, its location is uncontrollable. Okay, so they're isolated from each other, though they're connected continuously. If not continuously, at least periodically they should be connected. But they're ubiquitous nodes. They're everywhere once it gets deployed. So powering them through wall power is impossible. So you need battery power as a baseline, but we can go one step further, which we will not get into the details here. So what it means to be battery powered, the system that runs, that powers this entire sensor node or end equipment, IoT equipment, has to be low power in operation. It's a low power system, and circuit techniques are required to build them. There is a technology support required. I'll very briefly touch upon it, not go into the details again. And dynamic and static current consumption and optimization is important, right? And then they have to be autonomous. What it means to be autonomous, preferably they are self-powered. Of course, they can be battery powered, but it's not possible for you to go and change batteries, keep searching them where they are after deployment, and then go and find, okay, the battery is dead, I will change the battery. Many times, not all of them, many of them, majority of them, you will not have maintainability and repairability, and hence battery replacement is not possible. So can we get into energy scavenging or energy generation from environmental sources so that it doesn't have to be battery powered? There may be a necessary battery for critical application, but because it's not, the entire system is not running out of the battery life can be longer, but most of the operation is performed through energy scavenging, which means it has to be ultra low power, the whole system design, right? Of course, it has to be low cost and low bill of material count. What is bill of material? Various components that make up to make the system getting integrated and make it work, right? Low area, fully integrated system, obviously test cost and test time reduction, which again, it's a topic on its own. I won't get into the details on this in this presentation today. How the low power related test aspects can be understood, it's a field on its own. We can have a separate discussion on that. I won't get into it. Ultimately, it has to be cheaper to deploy as well as cheaper to replace, and in general, because they are difficult to maintain and repair, right? They're just repeating the same point. And of course, it has to be of longer age, not just that they consume low power so that the battery duration or it runs the same, the functionality can run with a longer duration of the battery, like longer life of the battery. Beyond that, the circuit itself should not age, deteriorate, and it get repaired or it get out of service. It should continue to operate as long as the power is available. If the power is available, there should not be any other problems with respect to its operation. So it should be of longer age. What is this age? The reliability and aging is another topic on its own. I would only like to stress here that the whole, for example, you create IoT end equipment, you put it on a wildlife, for example, on an elephant, you monitor it, you put it on a wireless sensor, right? So you cannot keep on changing batteries, and you cannot go and change every year the sensor also. You don't want to do that. You don't want to keep disturbing stuff, right? So it has to operate as long as possible, preferably 7 years, 10 years, or even longer, right? Of course, there are things about quality, reliability, and stuff like that. And whenever additional things are happening, all of this have to be tested. So complexity of testing increases. Again, that's not a focus of our topic today. In addition, this is all about the end equipments. Of course, there is a base station and hub, which we will not get into in today's discussion. And there is also safety and security aspects for both base station and this IoT end equipment systems. Again, those details we will not get into today. All that we will talk about, because they are isolated, autonomous, the requirement of being isolated, battery powered, autonomous, and low cost, and of longer age. I just established the requirement for why the whole system design has to be low power, right? That's all we are doing here. With that, I will maybe stop here for a couple of minutes if there are any questions before we go to the low power system design, the next section. We can make it interactive if needed. Maybe if there are questions in the chat, if there are critical ones, that will affect us moving forward without understanding them, I can take a few questions here, Vamsi. If there are none, I can move forward. Yeah, Vamsi, you can tell me, please. Yeah, am I audible? Either Vamsi or Sajal?
Yes, sir. Yes, sir.
Okay, good. Yeah. So then I assume there are no questions at this point in time. I'll just move forward. Okay. Here, I will not get into complete system design. I'll give you a framework for low power system design. What is the need for low? Okay, this foil, I think it got swapped here. I'm sorry. I just ignore it for the time being. I'll go directly here.
Sir, I have a doubt, sir.
Yeah, please go ahead.
Sir, like you told that IoT is our self-powered, no, sir? Sir, how is that? Like from laptop, it's getting powered, or how is that, sir?
No, the IoT doesn't necessarily have to be self-powered. I'm saying that is one of the requirements. If, for example, when you're remotely deploying IoT equipments, like for example, I told about the forest habitat management, or very small, difficult to handle devices that are deployed all across the place, ubiquitously deployed, it's going to be difficult being battery powered, because sometimes they may be too small or too difficult to maintain, too difficult to identify where they are and physically handle and replace batteries. They may even be smaller than a battery, for example, some nodes, right? So there are certain class of IoT equipments, end equipments, that can be self-powered. It doesn't mean all of them are necessarily self. Anything that's connected to your laptop wall power, there is no need for significant power reduction there. But yes, in general, even if they are wall powered, ultimately we want to be green. We want to overall reduce the power consumption of all the, because there is an explosion of electronic devices and equipments. You want to reduce the overall power. Otherwise, your power consumption, with billions of them getting deployed over a period of time. Now AI is coming in, edge AI may be a requirement. The compute power can be exploding. With all of this, if you don't get into low power, even in the laptop side and any of the edge side, even if you have very powerful battery, like in case of smartphones and laptops, and you have access to wall power, unless you drive for low power, we may not have enough power to drive all these devices. We might not have enough source of energy.
Thank you, sir.
Thank you. Any other questions? Okay. So quickly, jumping onto that, go to the system design aspect. These are the various, I assume many of you may know, basics of device physics, if not basic device understanding, CMOS or bipolar junction transistors, MOSFETs, PMOS and NMOSFETs. Fortunately, we had a previous session by Rajila. She gave a detailed introduction about the development of the evolution of electronics, including the devices, all the way from the vacuum tubes to the latest FinFETs, how things have evolved, how the overall the field of electronics were driven by the evolution in the devices. I assume that as a prerequisite, and you have understood reasonably what she has talked about. From there, we will pick here. So when we go, you all know, I mean, when you build some kind of electronic system, obviously, you know, you have power supplies, right? Maybe I will see if I can start with a quick block diagram and go back. Give me one moment, sorry. So that it becomes easy for you to appreciate. I'll just use this block diagram. I mean, it's not just a very high level, a conceptual block diagram. Say this is some kind of an SoC, system on chip, which has, as you see, all the yellow colored small boxes in the periphery, or IOs that are talking to each other. I mean, that enables interaction with the external world. And we have a lot of analog functions, oscillators, on-chip power management. There is a digital processor and other digital peripherals and on-chip memory, and all of these are integrated together in a single chip, in a single package or single chip, or a combination of them, and they all talk to each other, right? And obviously, you need all of this required power supply to run, and obviously you also need clocks. Predominantly, majority of the design is digital, right? And you know this today, the trend. Without getting into the details, I will just state some facts. Our predominant digital design, the framework is actually synchronous digital design. When it comes to synchronous digital design, you need clocks for time keeping, right? And also maintaining the performance. So you have on-chip oscillators or off-chip oscillators, a combination of them, PLLs, etc., to get required clocks of certain frequency. So the clocks control the activity, and the power supplies provide you the required energy and power for the circuits to operate. Right? This is just a very brief view of how the system looks like. With this, I will go here. I also assume, based on past discussions, if not, just take it as a fact, and you can go back and refer to your foundational texts and other literature to understand. This is a statement of fact for CMOS design in general. The power consumption is directly proportional to the capacitor, the effective capacitance where the activity is happening by charging and discharging, and whatever is the rail supply, the supply voltage level or the rail level between which the activity, the logic switching is happening between logic 1 and 0, etc. So that V square, and the frequency, which is not just the clock frequency, the frequency of operation, the activity upon which the data is moving. Of course, there will be clock and data will operate at different rates, and they will have different power components. But at a high level, given a particular node or a particular element, the power consumed by it will be related to capacitance, the effective capacitance, the voltage of the rail, and the frequency or activity factor. Right? Given this, what are the things that we can now control for power reduction? Is actually you can either reduce the overall capacitance, you can reduce the voltage level, or you can reduce the activity factor. Right? So there are various techniques to deal with them. The clock gating and data gating is a factor. This usually done at a system level, where if there are certain aspects, certain portions of the design or can operate at a lower frequency, or for a period of time, during a particular session, if they don't require, if certain section of the circuit is not necessarily required to be operational, you can stop the clock activity for that section, right? That's called clock gating. Basically, now for a portion of the design or for the entire design, for a duration, the clock activity will be 0, and hence the power of that section will be 0, which means only the leakage power will be dominant and there won't be dynamic power. Similarly, the same thing can be done on the data path. That's one aspect of active power reduction, right? And then you will have something on the power controls and power domain interfaces. This we will briefly touch upon. This is where these are more straightforward with respect to the concept, with respect to clock gating and data gating. But the power controls and power domain interfaces, I will come to it a little later. That will require functions and solutions like isolation, level shifting, and retention. I will go into the details of how and why they are required and motivate you towards that. And in the combination of, now you have the power supply level control and the activity control, which is frequency control and voltage control, right? That now can be done in a very fine-tuned way. That's called dynamic voltage and frequency scaling. So you can do, there is also another fact that when you reduce the voltage of operation, the leakage comes down. I mean, that's known from the equation. In addition, there are the technology dependencies, which I won't get into the details in today's presentation, is about the type of devices or the specific type of transistor types or device types that we are using. We have, and the technology with which they are processed and fabricated, they will have a very specific sensitivity to their maximum frequency of operation, right? So it's possible, but most of the times with a given technology, with a given properties, if a device is manufactured, when it goes to a lower voltage of operation, its performance deteriorates. It goes to a lower, it cannot operate at the highest possible frequency, right? These are certain information. And then there's about body bias. I will briefly talk about it later. So these are various aspects of low power design components, but some of this we will go into detail. Today, I will not get into clock gating. I think
Lakshman, there seems to be some question.
Yeah, please go ahead. I am not watching the chat, so please feel free to interrupt me.
Hi, Lakshman. Srinivas here.
Yes, you
okay. Yeah. So just I understand you don't want to go into data gating, clock gating. I understand, Lakshman, but data gating also you kind of talk about, because data gating is costly, is it not? And how do you get about that?
Yeah, data gating is specifically, mostly clock and data gating are at the architecture level, and they are truly not coming in the formal low power design flow, but they are handled in the design, the functional design itself.
Makes
Right?
sense. Well, that's what I'm thinking. Basically, data getting with RECAC or something like that, you kind of block it, right? But not at makes sense.
Yeah.
But then they will help the system level power aspects. I agree.
Yes,
Next.
dynamic power aspects. Yes, correctly.
Thank you.
Yeah. I think as we go, we will also understand why given the time, I'm limiting myself to a few aspects, few critical aspects of low power design.
Makes sense.
Clock gating in general is very well known. Even before the low power design techniques evolved, activity gating, reducing the dynamic power consumption is very well known. I won't get into the details of that right now. Okay. Okay, thanks a lot. I think, Srinivas, I answered your question briefly. Okay. Maybe a little more.
That's you did, Lakshmanan.
Okay. So these are some fundamentals. I mean, Rajila has talked about last month about the Moore's law that's related to scaling, and then the Dennard scaling that basically deals with the scaling of individual devices, right? The overall technology scaling. You have the length, channel length, thickness of oxide, width and wire, the width of the wire, and all these can be scaled in an appropriate manner. All these have been dealt in detail by Rajila in the last presentation, so I won't get into the details. But we got a very high level trend from Rajila when she discussed about the scaling, that obviously the area for a given functionality, you can compress more into the amount of given area, given die area, which means the individual device sizes are getting smaller, and hence you can put more and more devices into a smaller area. The length of the device into individual channel length is reducing, and hence and the thickness of gate is also reducing, and given all this and the oxide material and all these combinations makes it such that your operation voltage reduces, because your breakdown voltage can you cannot operate beyond a certain voltage. As you scale down in technology, it may just kill the device, right? The device may just burn, right? So the operating voltage reduces, their frequency of operation in general increases, right? And because the voltage reduces as well as default, the capacitance effectively reduces, the power also reduces. These are some trade-offs that she talked about, right? We will just keep it in mind moving forward. That will help us understand remembering these facts. Now there are a few other things that we need to understand: the voltage and bias levels. Why I differentiate between voltage and bias levels, I will show you some examples here with animation. So this is a simple CMOS inverter you would have all seen, right? Maybe most of you might have been aware of. But again, I'm going to make a fact, right? Just this in a CMOS technology. I'm not getting into all other TTL bijunction transistors, etc. Now that predominantly the world, the digital system design runs on CMOS technology, I will just limit myself to CMOS technology. This is a PMOS, this is a NMOS, this is a CMOS inverter, and there is an input and output shown here. What I want you to understand is, if the power supply is given, VDD and VSS, this inverter is appropriately powered, but for some reason, I'm not getting into the details of why, but if for some reason, if the input is floating, it's not connected to anything, there is no drive that puts this input in a known logic 0 or logic 1 state, or either closer to VDD or closer to VSS within the VT of the transistors, respective VT of the transistors, or much away from them. If they violate all of these conditions, and the input node can remain floating. When it remains floating, what it means is the physics takes over, and then because of the leakage, the relative leakage of the PMOS gate to VDD, and then the NMOS gate to ground, and then various other factors that are operating, the temperature and various other things, most of the times, you can take it almost 99.9% of the times, if you give enough time for it to settle, this node will settle to mid-rail of, when I say mid-rail, it won't be exactly VDD by 2, but there is a band around VDD by 2, right? So VDD minus VSS by 2 is the band around which the mid-rail will settle down because of its DC operating point. What it means, if the VDD is appropriately high, and when it is mid-rail, if the VDD minus VDD by 2 is higher than the VT of the PMOS transistor, similarly VDD by 2 minus 0 is higher than the VT of the NMOS transistor, both of them will be on, and it's going to consume, there's going to be a short current path. It can be called crowbar current, short circuit path, and various other names. But effectively what it means is, when a normal operation of the transistor or devices, this is going to consume certain amount of power, dynamic power, only during the activity when it charges and discharges. But under this condition, this is going to consume a DC current, which is limited only by the max capacity of these transistors, right? So there's going to be a huge amount of current that's, for example, just to get you an idea, if the dynamic power current consumption of this device, of this inverter for given capacitors and the voltage supply is about, say, 10 milliamps, right? Peak current, but average current, because it's peak, okay, I've not shown the waveform here, but with the average current of just a few milliamps or few microamps, the short current can be tens of even 2 or 3 orders of magnitude higher than the normal operating dynamic average current, right? I'm not talking about the peak, the dynamic current, I'm talking about the average activity here. Similarly, there are biases which are important. As you all know, many of you might have known, when you say take PMOS and NMOS, obviously they come with their bulk. NMOS can have a native substrate or may have a deep N-well, right, if it is isolated device. A PMOS have its N-well, so the well have to be biased at a certain voltage, right, for it not to cause inappropriate operation. And that voltage is also related by the forward bias voltage of the parasitic diodes between the source and the bulk or the well, right? So this, if they are not well controlled, they can again cause a huge current flow. If the predominantly we keep this parasitic diode in a reverse biased condition for normal operation. But if there are reasons where your bias voltage, the bulk bias voltage, are inappropriate, they are not, if VB is not less than VDD, things like that. I mean, if these conditions are not met, if these conditions are met, these are unsupported conditions, there can be a huge current flow, forward current flow in the diodes. And these currents again can be only limited by the maximum current capacity of the diode. And that can cause reliability issues, it can cause functional issues. And the third one is when such, as I talked about, there are different types of NMOS devices, isolated and unisolated devices. There are 2 NMOS devices I'm showing here. One is isolated, other is unisolated. Again, they may be called device with a deep N-well, device with a native device in a P substrate. Those are 2 different kind of NMOS devices. They may be used for noise purposes, noise isolation purposes, and threshold control purposes. But when different types of devices are sitting in a single chip for trade-offs and circuit optimization, if there are, it looks like silly mistakes can cause huge catastrophic issues, right? Again, I won't get into the details here. I'm just showing you examples. I've given references you can read, or we can get into details when you have a Q&A. Potentially, if you leave this, looks like very native, that the bulk, the N-well of this, deep N-well of this NMOS can be connected locally. But if this happens to be a non-isolated device, a native device, this connection is not possible, right? If you try to do that without your knowledge, no device can now identify. Your simulation will not show. Most of the checkers will not show. It will escape. And when you manufacture the device, it will have a short to ground, and that will cause both functional and high current issues. High current issues can be potentially catastrophic, causing very high currents burning the device, right? So these are some reasons why voltage and bias levels have to be appropriate. Now, with that background, I will go to system level example. So let's take, these are the 3 IPs which are connected together. They are talking to each other. These are IOs that are required for talking to external world. Now, this is example of a SOC. And the example I'm showing here is there is no power management. What I mean by power management is I'm not managing in a very detailed fashion the power consumption of each and every IP block or the whole system. I'm just allowing it to work in its native power consumption level that's entitled to. I have only one power supply, maybe at 5 volts, right? For example, that supplies every one of these elements here, individual components here. They're all operating at, say, 5 volts, and all of them in single voltage and a single maybe clock, and then it's going to consume certain amount of power. This is a baseline. We will start from here and then go next one. It is possible that this particular IP3, right? This could be your processor, right? This may not be required to continuously operate, right? Let's take an example of a smoke detector where this is the IP1 is your smoke sensor that has to be always on to sense the smoke. IP2 is some interface additional circuitry. IP3 is your processor and the wireless transmitter, etc., which requires a lot of power to operate. High performance is required, but they don't necessarily need to operate always. There is no functionality needed, and hence there is a possibility I can switch it off. So I can put a switch here in series to the power supply of the IP3, and I can switch it off. This makes the IP3 switched off, and then all the leakage and dynamic power from this is completely cut off. There is no power consumption now because there's no power. So the battery sees the IP1 and IP2 and IO. Those are the only power supply consumptions, power consumptions that are seen by the battery. IP3 is completely cut off from the primary source. But as you see here, this IP3 is now cut off. If you give a long time, this rail can settle to ground because of the leakage, right? And which means any output signals going from IP3 can be seen as floating. So now you understand why I introduced CMOS floating in the previous example as one of the scenarios. When it's floating, what happens? This can be mid-rail, right? Even though the supply is IP3 is off here, it still connects to gates on the IP2, which is powered, right? The leakage of these gates are PMOS and NMOS gates, and all of this, which are connected to this, are going to control what voltage at which this input settles, because there is no active drive from the actual drivers in IP3 because they are powered off, right? Now this can cause floating nodes, which can cause high currents, it can cause functional issues. So this is one problem, right? So you have a power switch, it causes power islands, and there are interface issues because of that. Now you also have sequential elements inside this IP3, which could be just one flip-flop, or it could be thousands of bits of very deep and broad memory, right? Now, if you have to bring the whole system to a specific context, right? Whenever I switch on the switch IP3, I cannot use the IP3 for its required functionality immediately. I need to make, if there are thousands of these memory elements, I need to program all of them to a required state before this IP3 can be operational usefully, right? Because it lost its state when I powered off, right? Now, is this context important? And how fast is this context to be recovered when the power is up? These are two critical aspects in the system design, right? And then third, it is also possible that earlier, you see IP1, 2, 3, all of them are in safe supply. Even though I've switched off IP3, once they're on, they're all operating at the same voltage, same supply voltage. But it's possible that I really don't need to operate IP2 and IP3 at that high 5 volts, 5 volt. If appropriate devices are available, different types of technology devices are available, I can use appropriate devices to gain maximum performance at an area at the lowest possible power, because V square is also the active power. It's proportional to active power. So I can reduce the active power and also leakage power by reducing the power supply voltage of IP2 and IP3. For that, I introduce the on-chip supply. So now, as you see, IOs and IP1s are all operating at a standard voltage, so that because this IO has to interoperable with external devices, which may all operate at a standard voltage level, right? But what is completely internal, I can keep it at any voltage level that's sufficient for my performance and power consumption. I can operate at a different voltage. It may be 5 volts. This rail that's powering IP2 and IP3 can be at 3 volts or 1 volts or 1.8 volts, whatever it is. So I can do that. But when I do this, again, there are interfaces that's coming here. There are voltage islands, and there is now, it may be a 1 volt output that's talking to a 5 volt input or vice versa, right? Obviously, their logic levels are not compatible. They're either functionally cannot be comprehended by the receiving system, or if they happen to be in the mid rail, if the voltage levels, it can also cause a huge current flow and cause reliability issues. So in general, these are the various aspects when you try to reduce the power through the systematic means of power gating. This is power gating, and then various on-chip supplies and voltage islands that you're creating, right? With that, what is the solution for that? Again, without getting into the circuit level details, at system level, there is a concept called isolation. Conceptually, what it does is I can have cells only at the interface. It may have billions of nodes inside the IP3, but I may have just 100 or 1,000 nodes that are talking to external world. Outside the IP3 to other IPs, which may be on. Only those primary interfaces, I can control such a way that they are defined in a known voltage level or safe voltage level, safe logic level, right, with a control signal saying I'm isolating the signal so that the system will not see undefined voltages. So that's called isolation. There are various types of them. I won't get into the details in this meeting, in this presentation, in the interest of time. And then for the context, there is something called retention element, where there are flip-flops that can be designed such a way that only a small portion of the flip-flop can be powered while majority of it can be off, so that it can retain the previous state. So even if you have thousands and millions of these flip-flops, as soon as I power on, and I have a control signal called retention here, when I enable, I'm coming out of retention, I can restore the state before I switched off whatever state in which I saved for this flip-flop. The same state I can restore in just one clock cycle or less than one clock cycle, right? So this is a way to restore the state, but all this, it doesn't mean they will all operate without power supply. Only those small sections of the device, it's a fraction of the entire circuit that may be powered to keep those states in a safe state or to keep the previous state. But rest of the circuits are all off, so power is still saved. At the same time, I'm able to wake up very fast when I'm powering up and start working seamlessly. And finally, when there are multiple voltage levels, you have the concept of level shifting that safely translates logic 1 levels and logic 0 levels between two different voltage units. That cells are shown here as level shifters. So these are, and obviously all of this have control signals. You have red, you have the switch has a control signal, power switch. The retention has a red control signal, isolation has isolation control signal, etc. This level shifting can also be with, if they can switch off the on-chip supply on and off, and they can have both power and voltage domains here. Then it may also be, it may also have a control signal to have a unified isolation plus level shifting behavior here. So all these control signals have to be controlled by a sequencer here. There is some kind of on-chip sequencer that sequences in an appropriate way. And then there are analog and other IPs integrated to this. So this shows how the whole low power system is integrated. But many of the aspects that I talked about here, right, like the power switch, retention, isolation, level shifting, all of this, and also analog elements like on-chip supply, AIPs, power, IO, I mean, their power supply connections, right? I'm showing here all the power supply connections in dotted lines, right? They're not, why I'm showing in dotted lines, we will see it in the next page. So all of this, usually in your semi-custom design flow, today we use for digital system design, we use a RTL view, which is register transfer logic level in which you write the functionality. There we don't have a concept of power supply, analog, I mean, either analog or digital power supplies, isolation, retention, etc. Whatever we talked about that are required to handle low power system design, these doesn't exist. There is no way to capture them in RTL. You can capture them in a very hard-coded way, but it will become very, very complicated, right? Still, the power supply connections cannot be handled, right? And verification becomes very difficult. It becomes extremely complex because these are thousands or millions of such nodes that we have to handle, and there are tens or hundreds of power and voltage islands. This is very difficult to handle manually, right? So then we bring in what is called a power intent. Maybe I will take 5 to 10 minutes to just 2-3 minutes for giving you a power intent, and then the verification aspects at a very high level, the complexity of it to introduce you. What is power intent? Power intent is whatever that is not there in RTL that we saw before in the previous screen, right? I mean, here, only the basic logic functionality is what is captured in RTL, right? But for low power design, we need various other aspects, including the power connectivity, power supply connectivity of multiple power rails, multiple voltage rails, level shifting, isolation, retention, power sequencing behavior. Power sequencing behavior itself will be available in RTL, but there are certain aspects of that which I will not go into the details today in the interest of time. And then the bias, the bulk biases and things like that we talked about in earlier examples, well biases, all of this are not available in RTL. All these can only be captured in a different way that's called a power intent, right? I'm sorry. So all those dotted lines are coming from power intent. And then this shows when you do a system integration, what's required. The power intent can be today, predominantly, there are two standards of power intent. One is CPF and other is a UPF. CPF is the common power format predominantly used in cadence-based flows, though it's standard, but not widely supported. But there is, for last 10 to 15 years, there is another matured as well as evolving standard called UPF P1801. It's IEEE standard called 1801. That is called UPF. Both of them have equivalent behaviors, equivalent constructs, right? Any of these formats can be used to capture power intent. I won't get into the syntactical details of this in today's discussion again, right? All that we are saying is this whole, whatever I'm showing in the picture here, the entire top level instances of IOs, instances of analog without their power connectivity, only the signal connectivity and the complete digital behavior without power connectivity, all of this is captured in the RTL view, right? And then for all the analog IP and mixed signal IPs, their boundary conditions are captured because they're unsynthesizable, they're only simulatable. Their boundary conditions are enough for integration. They are captured in a black box view. It could be Verilog AMS, it could be .lib, it could be macro CPF or UPF power models and things like that, right? I just made this very generic, so the specific CPF and UPF related comments I'm not explicitly making in the PPT, but of course I can annotate them. And then you have the detailed power intent called design CPF or UPF is used to capture the top level RTL and the RTL designs. They are called detailed power intent, where the requirement for retention, isolation, everything is specified in this detailed PI, right? And then you have the macro, black box or macro CPF or the power model UPFs are used just to capture the boundary information of analog IPs and mixed signal IPs and hard IPs, which are not synthesized and getting implemented, which are pre-implemented and just getting integrated into the system in the RTL phase, right? So these are the various views that are required to integrate. These are the information that are captured there, and they talk to each other. In case of a verification setup, in addition, we also have black box view is not sufficient anymore, because black box view will provide only boundary information that's good enough for integration and physical design. But when it comes to simulation, you really need to know how any input behavior change, input signal change will change the output signature, right? So the complete glass box view is needed. So you have a functional view, which is your Verilog or VHDL model of analog IPs and IOs and hard IPs are required, along with annotation of a macro CPF or power model UPF, so that both the power information and functional information are annotated on top of each other. Together they talk to each other. So this is how the simulation view look like. And then there is something called a test bench level CPF or UPF needed, right? So this is now, as you look at, I'm just showing what we started with. Clock gating, data gating, usually they are handled in the native functional RTL coding itself, RTL design itself. And power intent deals with isolation, level shifting, retention, etc. It doesn't mean you cannot handle them in RTL, but it becomes very complex. But people use very advanced level of designers use actually design methodologies use some portion of isolation, level shifter, retention can also be done in a custom way in RTL, but it requires additional verification requirements, very careful design methodology, right? And obviously the power control and sequencing is coming from the functionality of the entire architecture. So that's how it looks like. Now, very briefly, couple of minutes, I will show you the complexity and requirement for low power simulation and verification. Meanwhile, if I can take, now we are just close to the end time. If you want, it's a logical time, I can take a couple of questions before I move to the verification topic.
Hello?
Hello, yeah?
This is Girish here.
Yeah, Girish, yes.
Yeah, just a question regarding that isolation, whatever you have shown.
Yeah.
So instead of that, can you just use a pull down resistor at the input? Would that be sufficient?
Yeah, you can see for functionality, Girish, pull down resistor can be used. It will define the value. But think of it when the power comes back at IP3. Okay? Then whenever you are driving a logic, assume you are having your safe state is 0, no problem, right? Normally this IP3, when it operates, it only have a dynamic power, right? Of course, leakage power and dynamic power. When you have a permanently connected resistor, for the purposes of when IP3 is off, that all of these resistors are going to consume dynamic power and static power whenever the logic 1 is driven from as output of IP3. That's going to increase your dynamic power heavily.
Okay, but how does this isolation circuit looks? Even it's also made of transistor. I don't know how actually
it's made of transistor. It's made of transistor, but as you know, transistors, your CMOS design in general, to keep a logic 0 or 1 state, You don't need a permanent current. It only charges the parasitic cap and then it keeps the state.
So you're saying that using pull down resistors will be more expensive than using
It is
isolated?
expensive with respect to area.
Yeah,
It's
and
expensive
power.
with respect to power.
Yeah. Okay, fine. Thank you.
Yeah, obviously we can go to the details of the isolation cell, how retention cells are designed. There we can look at the details, but at a gross level, resistors, they did a job earlier in custom low power design. Actually, they're not low power design, custom integration of a safe designs without reliability problems, with functional designs, without care for power, right? Once the low power requirements come, the resistors cannot do the job anymore. They are now dynamic kind of pull downs, as you see.
Okay, thank you.
Yeah, if there are no other questions, I will quickly go to the simulation aspects of it. So as I already shown, this is our test bench. We have seen a system. Now this is our system, obviously test bench looks like, which is similar to your actual test setup when a real IC comes out, right? In a lab, in a PCB or a breadboard, right? So you have the power supplies, passives that are connected, loads that are connected, and you have bus function models that are required for providing appropriate stimulus and observers for looking at signatures, etc. And it's possible when you need more accuracy where analog circuits are needed, you may keep them in spice level or transistor level, which may be slower but more accurate. Those sections of them get simulated accurately. And then when you have analog mixed signal aspects, when both analog and digital simulates together, the signals transitioning between them will require some kind of a connect module to translate them. But I'm only giving you the names of some of the techniques or components here without getting into why they are needed in the interest of time. This is how overall co-simulation, low power co-simulation setup looks like. With that, we have already seen that these kind of issues that can exist, right? In addition to basic functionality, we also need to make sure in verification such problems don't exist, right? So that there won't be reliability issues. So it's much more than in a normal RTL functional design, you're only verifying functionality. If you give, say you have an AND gate, you give all 4 possibilities of inputs A and B, whether your output Y is following your truth table. And if the timing is meeting, the settling times are meeting your timing requirements and performance requirements. Those are the primary 2 things. Of course, there are next level reliability things, but when you bring into low power aspects, it's much more important because you have multiple voltage levels. There are on and off domains talking to each other, things like that. So you have to be very careful when there are tens or hundreds of domains that are switched on, off, and combinations of them are interacting. You have to make sure there is none of the inputs are floating to a always on domain, and biases are not by mistake going to unsupported voltage levels or switched off by mistake, things like that, right? So I'm not going to the text here. Whatever I told you verbally is what the intent of this particular slide is. So these are the problems also we need to look for, right? I think I will skip this section. I will go directly to a quick 1 or 2 page summary of the simulation setup. The need for low power verification, as you see here, we already saw increased. The complexity is increased when you have multiple power switch domains and multiple clock frequencies, and obviously depending on your performance requirement, different sections of the design can operate at different clock frequencies so that your dynamism activity factor can be controlled and power can be appropriately managed, right? With all of this, you have thousands, if not tens and thousands or millions of clocking and power modes that are there. So you have to verify your entire chip operation across all these modes, right? In a normal unmanaged power, you just have to check the entire functionality of the chip or the design in only one mode. Now the same set of or subset of these functionalities have to be verified along with their reliability requirements, other unsupported conditions, etc., across tens of thousands of modes that you have to repeat those scenarios in. So that's a complexity. And I will show just one more page and then I will leave you there just to show again the complexity. This is how, this is one example of how overall verification flow looks like. Obviously, I mean, again, don't worry about the make aspect here. It's basically the basic environment that's a regression manager. It can be make or something else based in Unix or Linux or Windows based machines, but predominantly it's Unix or Linux based. And then you have test bench. which can have a combination of digital. And whatever I'm showing here, what is in red is all purely digital. Whatever is in blue, it's purely analog. When there is a transition between digital, I mean, red to blue, there is a mix of analog and digital contents that are mixed together here. So you have SPICE models and libraries needed if there is analog mixed signal simulations needed, IMS configuration. You have a test bench that can contain both analogous contents and digital contents. RTL or gate level simulation, depending on whether it's a initial RTL level simulation, functional simulation, or you're doing a detailed timing simulation post implementation. Their appropriate netlists and RTLs are used, which are predominantly digital in nature. Though their functionalities, if there are analog IPs or mixed signal IPs integrated into them, those functionalities are coming from their appropriate behavioral models, which can have both analog and digital abstractions together. And then you will have parasitic timing annotation, and then you have simulator configuration, all of this. And all of this are associated with the CPF or UPF power intent. For each of these different kinds of power intent, for analog and mixed signal and hard IPs, you will use black box power intent or a macro CPF or a power model UPF. And for RTLs, you will use a detailed, what do you call it, the design CPF or detailed CPF or UPF. And then gate level, when you go to power connected gate level, you won't use any power intent, because the power connection and full implementation of including retention, isolation, level shifting, power switch, etc., they're already there in the netlist, right? Including their gate level abstraction. So this is how the system looks like. And I will show here for a system that I shown examples there, how the overall, I'm just showing only the power up functionality and just to highlight the complexity of simulations here. This complexity is same. It's not just complexity of simulation. This is how even the chip works when you test it in real field. But when it comes to simulation, it's a lot of activity, a lot of computation, and a lot of details that you have to take care, so it becomes more complex, right? At a high level, I'm showing here the initial power up phase followed by analog bring up. What it's mean by analog bring up is the on-chip oscillators, on-chip power supplies, and all these things that come up. On-chip IPs are coming up. On-chip oscillators settle to a final frequency, because obviously any circuit will have a settling time. The oscillators settle to a valid frequency of operation for the determined and what do you call it, required performance. And then the chip reset is released, followed by the system. Once the reset is released, the on-chip software can take over. You have seen there is a digital and then on-chip power, memories like non-volatile and volatile memories that are integrated. Now you can have your instructions or programs programmed onto the on-chip non-volatile memories, are loaded from external memories into the on-chip RAM, and then your system is getting configured and the software, actual functional software, the application software start running. This is how the whole system flow looks like. Now, if you have two primary inputs which are powered by the battery, then you have a battery supply that comes up at V function level. V func is just, I'm not giving numbers here. It could be just 5 volts. The second one could also be 5 volts, but it's a separate, it comes in a different sequence. There are two different primary sources that are coming out, and VDD in2 and VDD IO are connected together. They're all coming up. Once it comes up on the primary supplies, the internal on-chip power management and oscillators start operating. There can be temporary oscillators, low accuracy, high power oscillators that are used for timekeeping for a short period of time until the more accurate oscillators come up. And then multiple internal analog supply, mixed signal supply, digital supply, memory supplies, all of this, it should be on-chip supplies that I've shown in the block diagram. All of this can come either together or in a sequence, right? They come at different voltage levels. It could be analog could be at 3 volts, mixed signal can be at 1.8, digital can be at 1.2 volts. And then the actual high accuracy oscillators are starting to settle down, and then they stabilize in their frequency. Once the frequency is confirmed to be stable and all other functionalities, basic behavior is powered up properly, the on-chip reset is released based on, it could be also controlled from an external chip enable signal, or may not be controlled by it. I'm not showing that in this picture here. So now the reset is released. Once the reset is released, now there is system configuration that happens. Could be boot process from NVM to rest of the stuff, and then the programming is actually starting here. When you start user programming, it's possible that you have a separate power domain like VDD IP1, VDD IP2, different IPs. They are powered as required, powered up and powered down as required. So this is the complexity of the design. So many of the aspects that I'm showing in the white dotted box are complete power modes are considered for SOC and verification through power intent. But what's difficult in the existing integration flows are the analog power up part, right? They are not, in spite of your using power intent and sequencing and everything, this section is not verified in the formal verification as well as simulation-based verification aspects. So these require what is called a mixed signal verification for making sure that they're operating as spec'd and as intended. There are developments in formal verification which are not yet to the level where they can be used for verification. There are formal verification flows which I'm not talking about here. And quickly at the end, that's pretty much what I have. So right, I mean, so there are some guidelines. I won't get into the details of this again. To close the talk, analog and power are key drivers for many mixed signal SOC designs today. There are several critical challenges for low power integration and verification, especially with mixed signal integration. There is a need for need to comprehend and understand and manage inconsistencies across flows. I mean, the flows have to be consistent across implementation, verification, custom and semi-custom flows, standard cell building, and then at RTL level and gate level across entire different phases, right? And they have to be consistent and comprehensive low power mixed signal design and verification framework that's actually illustrated as an example here. And there are some future directions. I won't talk about it in the interest of time. So that's, I have given some references. You can go through if required. I can take some questions. Sorry for the delay in closing it. And yeah, we can take some questions. Very quickly, thanks a lot, Sajal and Vamsi and all the team, Girish and team for this opportunity, and several colleagues and collaborators who have also helped me with respect to this content and the knowledge behind it. Thanks a lot.
Thank you, sir. Participants, if you have any questions, please feel free to do the unmute, or else you can keep it in the chat box.
Lakshman, can you just show that references slide? Just one.
Yeah, some of them are some DAC papers. Many of them are mine. Some of them are different. So many of them are from DAC and CDN Live and DVCon kind of conferences.
Thanks.
And the whole of this, as I told also, this entire flow in much more detail is also available as this content itself is derived from a 2019 tutorial in this DAC 2019. So that's given by me. So this source, pretty much most of the content, some slight modifications are there, but this is sourced from that.
Lakshman, you can share this PPT, right? Like people are asking.
Pardon, I'm sharing already. I'm sorry.
No. After this session, PPT.
Yeah, sure, definitely. Yes, this presentation is custom made for this. I can share. Yeah. Okay.
Sure. Okay, participant, please unmute yourself if you have any questions. I think it's a great chance to interact with Lakshman. You can connect with him over LinkedIn. You can discuss something.
And also, depending on the time, if participants can briefly introduce your name and your student or industry and what's your background, so that will help me understand and explain the questions in a little more as appropriate.
Yeah.
Feel free.
Do we have any questions? Okay.
Sir, I guess we don't have any questions.
Okay.
Lakshman sir, can you stop sharing? I will share my screen.
Sure. You don't say stop sharing. You can take.
Can you see my screen?
Yes, I can see.
Yeah, thank you so much, Lakshmanan sir, for your kind presentation. And I hope it's an interactive session. Even I have observed 2 to 3 people in the mid of the presentation. They had their questions raised right away. And Sajal sir, any add-ons?
No, nothing. Thank you, Lakshman, and thank you everyone for participation and had a good interaction.
Yeah, thank you very much. Thanks for the opportunity, and it was nice. Yeah, we could have had a longer time for interaction, but I think like it's very late already, too late in the night, and then thank you.
But definitely, you can connect with Lakshman later and have the discussion. Please go ahead, Vamsi.
Requesting everyone to fill the feedback form for if you want the certificate. And please remember, the certificate will only be sent for the CEDA members. And the same feedback link will be shared via email to the attended participants after we got the attendance from the group meet. And yeah, that's pretty much. I request everyone to switch on the cam so that I can take one quick pic.
Request everyone to please turn on the cameras if possible. That's it. Huh?
Just remind you. Okay. On a count of 3, 2, 1, please give a smile. I'll take one more. Just a minute. Again, on a count of 3, 2, 1, smile. Yeah, thank you so much, guys. Yeah, thank you for attending. In the next month, we will come up with one more session. It will be on layout. The details will be shared soon.
Okay.
Thank you, Lakshman. Very good.
Thank you. Bye.
Thank you.
Have a nice day.